Kimmy's, Mr. Bake, Joker. Very good. Tonight is your night. I'll let you swallow your Whopper, though. You ready? We are going to derive the diffusion equation. In chemical engineering, where do you start? What do you start with? Mass balance. Okay, we start with mass balance. And then what else do we need? We need an equation of motion, an equation of state. What else? Fick's law. We're not going to assume concentration gradients here. Good answer. I'm thinking more we need a constitutive equation. Okay, but we don't need a constitutive equation. Why? Because we're going to assume a Newtonian fluid. Okay, and we also need an energy balance. But this system is not going to do any work, so the constitutive equation and the energy balance aren't necessary. But the first and foremost is what? The mass balance. And we talked about this before, that, and maybe I didn't make this exactly clear, but a long time ago I had a project where we knew that we had massive well interference. So you cannot perform material balance on a single well unless that is the only well in the reservoir. So we began working on this project thinking, well, we can somehow compensate for this. And it turns out you can't. Excuse me. So what I did was I created a leaky material balance model. Bad idea. Okay? Nobody in here is Russian, right? So we're going to talk about the Russian space program for a second. Do you guys remember how many engines did the Saturn V rocket have? I'll give you a hint. Okay? How many engines did the Russian launch vehicle have? Nobody remembers? I believe it was 31. And they were in a circle. And every now and then, one of them wouldn't fire. And what happens? Exactly. It flipped over. So, simple things. Whenever you violate material balance, something bad's going to happen. The Russians tended to use just a bigger hammer, right? Everything they did, bigger. But that 31 engines, or whatever it was, turned out to be a bad idea. Now, the pattern that the Saturn V engines were in, if one failed, which thank God they never did, it would still be okay. But it didn't work out that way. On the other hand, what's the famous story about the American space program? They spent millions creating a pen that would write in space. And what did the Russians do? They used a pencil, right? Okay, pretty good. Interesting. I'm also reading a story right now that has nothing to do with the previous thing, but is about the space program. The Russians had an incredibly difficult time with their docking system. The Americans did too, but for a slightly different reason. They could, the Americans knew whenever the Russians could not actually dock, that there was no way they could go to the moon. And so they were years behind. It was just an interesting little tidbit. At that point, the Americans said, you know, we can go. We know we can do this, so that's a step. The Americans also did something else that was really bold. Once they started with Apollo 8, everything, the entire system was a test. They didn't try a piece of it. They just did the whole thing at once. And the guy who led the program said, if they can't do this, they can't get, it won't succeed anyway. You can't test this thing in pieces. You have to do the whole thing at once. Okay, so why do something like that? Why think about something like that for tonight? We need a material balance equation. It has to be relevant. We need an equation of motion. It has to be relevant. The equation of motion can be a little bit of a cheat, let's say. Equation of state. What's a good equation of state? Real gas law, ideal gas law, any other equations of state? What's the simplest one? Alex? Okay, I would too. What about for a liquid? We've been talking about it all week. constant compressibility liquid. Okay, so we don't really talk about it here, but that is what we're going to use. We're going to use a constant compressibility liquid. So it means that all the energy in the system comes from the expansion of the liquid. Okay, I know that we're going to add a little bit for rock expansion, but for the most part, it's going to be the expansion of the liquid. How are we going to marry these together? What's another name for the equation of motion? Does anybody remember? Darcy's law. So we're going to have a material balance or a mass balance relationship, and on the left-hand side, there's a velocity term because it's velocity times density, right? Momentum or mass flux, rather. And we're going to substitute the velocity term from Darcy's law into there. What will we assume about Darcy's law in order to simplify this? Well, it's a liquid case. What assumptions can we make? Viscosity is constant and permeability is constant. So we'll get to that in a minute, but we'll do that. And what's the derivative of a constant? Well, 0. But what's the derivative of a constant multiplied by something? Well, you pull the constant out. So this is all going to work out nicely. Now, on the right-hand side, we have what? Porosity times density, which is mass. What happens when we differentiate porosity multiplied by density? Let's say we differentiate it with respect to anything. We're going to have to use the product rule. Okay? So what we're going to first do is we're going to take the derivative of porosity times density with respect to time, because that's what the material balance or the mass balance is. And then we're not really interested in the derivative of density with respect to time or the derivative of porosity with respect to time. What are we interested in? The derivative of pressure. So how do we expand that derivative? We're going to use a chain rule. So first product rule, then the chain rule. Okay? Very good. You guys got it. This will be quick. Okay? We have to state this in words, that the rate of mass flow into the system during the interval delta t minus the rate of mass flow out of the system during the interval t delta t is equal to the rate of mass accumulation in the system during the interval delta t. Joker and Mr. Bake. Is this correct? This is the most fundamental thing that you learn in transport phenomena. Can mass accumulate in a system? Yep, it can accumulate. All right? So we're going to have mass accumulation in the system. If mass does not accumulate in the system, what kind of relationship is that? Steady state. Very good, Joker. Big hug. Okay? So the mathematical expression for this is this a derivative operator, del dot rho v, is equal to the negative of the derivative of porosity multiplied by density with respect to time. And of course, this is a partial derivative. We'll talk about what this del dot thing is. It's a shorthand. You guys understand shorthand? What systems are we interested in? Radial flow? Sure. Linear flow? Sure. Spherical flow? Sure. Radial flow with tangential components? Sure. Radial flow with vertical flow components? Sure. We're going to simplify it, but this is how do you derive these? Do you guys remember, Mr. Bake? You forgot. Joker? Shell balance. Do you remember shell balances? Did you enjoy shell balances? Almost as much as translation of coordinates. I don't think I ever hated anything as much as translation of coordinates, but shell balances were right up there. So actually, when you take Chemical Engineering 629, you will derive all the del dot products for the different geometries. But for right now, it's just bookkeeping or shorthand. Okay? And then Darcy's law for the there is a horizontal form, and it's just going to be, we'll eliminate the gravity term, but it's permeability divided by viscosity multiplied by the pressure gradient. Okay? The equation of state is simply described as this. It is 1 over density, the derivative of density with respect to pressure, and that is a constant. Cameron, is that really a constant? No. But we can assume it's a constant, can't we? We can force this problem to have a constant compressibility. Okay? We can force this problem. How constant does it have to be? Does it have to be 1%, 10%? Well, we'll talk about that. What's the penalty for it not being constant? Very good. It will be a non-linearity. And it's a function of pressure. But pressure is a function of time. So it is implicitly a function of time. Hence, that's where the non-linearity is. The function that you need to know is a function of the thing you're solving for. That's the definition of a non-linearity. Let's think about it. In other words, if any of the coefficients are pressure dependent, it's nonlinear. Is viscosity dependent on pressure, Gabe? For a liquid? What about for a gas? Hell yeah. Okay. But for the liquid case, we'll probably get away with it. Is the compressibility constant, class? For a liquid, we can get away with it. What about for a gas? No way. Okay. So what's going to happen for a liquid? Well, we just assume a bunch of things are constant, and if we're lucky, life will be good. What about for gas? And it's already 8:30, and I was going to try to cover gas tonight, but I'm not. I'll wait till tomorrow. What's going to happen for gas? You can bet. Everything's going to be a function of pressure. Okay. What's rule number 0? Trampa. Cheat. Okay. Tomorrow night when we talk about gas, how can we cheat? We can assume that the viscosity z-factor product is constant. We can assume that pressure divided by the viscosity z-factor product is constant. What else can we assume? We can assume nothing, and we can solve it with pressure, z-factor, and viscosity in a special variable. And what is that special variable is going to be? It's going to be pseudo-pressure. We've already derived the pseudo-pressure transform for steady state flow. By definition, if your brain's functioning, it has to be the same for every condition. So pseudo-pressure will drop out of the derivation tomorrow night for the gas diffusivity equation. Can we also have a pseudo-pressure for oil? Has anybody read ahead? Okay. Can we? Of course. Okay. Who derived the first pseudo-pressure formulation for oil? Everybody's thinking, was it Levine and Pratt? Was it Vetkovich? Was it somebody else? Who was it? It was Evinger and Muscat. What year? Something like 1943. They derived it, and they sat there and stared at it and go, we don't know how to evaluate this. So we'll assume it's constant and move on. Okay. Again, mass balance, equation of motion, equation of state. We got all our pieces. Joker, pick on your worst enemy in the class. You're not going to admit you have an enemy? Why are you looking at Mr. Sarkar? Mr. Sarkar, are you guys enemies? You are now. Okay. Mr. Sarkar, do you like jigsaw puzzles? Not really. Oh, you do? You do like them? Have you ever taken the jigsaw puzzle and flipped it over so it's all brown? No? You never thought of doing that? Okay. Well, that's what tonight's going to be like if you're not paying attention. Because this is a jigsaw puzzle. It only has 3 pieces. Remember when you were a kid, the puzzles had like 4 pieces? And you're like, what do I do? Mommy, daddy. Okay, well, there's only 3 pieces here. And they will fit together if you'll pay attention. Tomorrow night it gets a little weird, and the next night it just gets bone crazy. But for tonight, we have 3 pieces. Let's see if we can get them together. Okay. We do have one little tiny problem. Ricardo, we assume a constant compressibility, right? The math all works out, but we have a leftover term. And that leftover term is compressibility multiplied by the gradient squared. Okay, Joker, pick your best friend in the class. Is it? He doesn't look very happy to be your friend. All right, Cam, you ready? Take a deep breath, close your eyes, go to a happy place, and think about this. You'll be happier if you close your eyes. So we have a function of pressure multiplied by the gradient squared. Is that nonlinear? It violates just about everything. Do you remember the definitions of nonlinearity from the discussion that Alex would have had with you? What's one? You can open your eyes. I'm afraid you're going to fall asleep. What's the first definition of nonlinearity? A function of pressure multiplied by a function of pressure. What's the number one rule? You can have no function raised to a power higher than 1, right? Or different than 1. I think gradient squared is a really bad sign. And then compressibility multiplied by gradient squared is even more nonlinear. What's rule number 0? Who wants this one? Can? What's rule number 0? Cheat. So compressibility, if it's small, really small, then small things multiplied by something is usually small. What if the gradient is also small? What happens, Mr. Liu, when you square something small? Smaller. And then you multiply it by something small. It's even smaller. Okay? Math ladies, you don't like this. You think nonlinearities need to be accounted for. You're going, you can't just do this, you bunch of stupid petroleum engineers. You can't just say, I assume it's constant. Go away, you know. All right? You agree with that? You can't just do that? But tonight, we're going to do it. We're going to say, just go away. Is the world a better place? I don't know. Can you imagine? Give me an example of where this is going to be a problem. Man, that's a tough question. I don't think so. I don't think so. I don't think the gradients, because you have a huge fracture system, I don't think the gradient, I mean, yes, the gradients in the formation near the fracture face are high. I don't deny that. But I think the aggregate behavior, because you see linear flow, for example, you would not see linear flow if this condition were to affect that, right? Because you would have another relationship. Anybody else? Heavy oil could be. I hadn't really thought of that. That's a good guess. But what's the most likely culprit of this term not being negligible? This is liquid. Sorry? High rates. Okay? But they'd have to be really high. And the oil would also have to be fairly light, fairly spongy. So, you know, life's pretty tough right now in the North Sea. They have 400 platforms. The Karnes County, Texas produces more oil than the North Sea. Did you guys know that? The Eagle Ford Shale. One county in Texas produces more oil than all of the North Sea. That's pretty scary. When they first brought the wells on in the North Sea, some of their rates were 10,000 barrels a day. And these are not extremely high. There are some high permeability, but these are not extremely high permeability wells. And in particular, there were a couple of people, Adnoy and I'm losing my mind. I forgot his co-worker's name. Adnoy is actually a mathematician who I believe became a drilling engineer. But he solved this problem using perturbation to account for this term because they were looking at high rates. What does perturbation mean, ladies? You cheat. You have a trial solution that you add on, and it creates. So you have the base solution, which assumes this is 0, and then you have a first-order approximation that's added to it. This is kind of a clever math trick. It doesn't work very well, but that's okay. Do you know how to make that term go away completely? Define a pseudo-pressure for oil, and it goes away. Define a pseudo-pressure for gas, and it goes away. Okay. But we probably will get away without really having to worry about this. Nobody's asked me what this del squared thing is. And again, that's that geometry component. It's a derivative. Okay, we'll talk about that in a moment. It is an operator, if you want to think about it. So if we assume small and constant compressibility and small pressure gradients, we end up only with this term. And again, Adnoy, and I apologize, I forgot his pal's name, they derived a formulation to solve this as a perturbation solution. But, you know, again, it's a very low order approximation. So very quickly, we do have an oil pseudo-pressure. And as I mentioned before, the first form of this was 1943 plus or minus, Evinger and Muscat. The alternate form is here. You can have permeability as a function of pressure, correct? It's actually a function of saturation, but saturation is a function of pressure. There's a lot of twisted relationships here. Okay? And then finally, we have something called pseudo-time, which we haven't talked about before, but Joker had me on the spot with this one, because the compressibility of a gas is not going to be constant. In fact, it's going to be highly nonlinear. The viscosity of a gas is not going to be constant. It's going to be highly nonlinear. You multiply the viscosity by the compressibility and you pray that that's constant. It didn't work that way. Okay, this is a really bad deal. This integral is extremely hard to evaluate. Why? Because pressure is the thing you're solving for, and the pseudo time function is defined in terms of pressure. Uh-oh. So how do you solve a nonlinear partial differential equation, class? You can either cheat, as we've discussed, you can cheat on half of it, or you can cheat on all of it and assume that that compressibility function is constant, compressibility viscosity function. What's the right way to solve it numerically? Okay. And in fact, Aronofsky and Jenkins invented numerical simulation, or maybe Levine and Prats, whoever you want to argue, but we'll say Aronofsky and Jenkins, because they could not solve the gas problem analytically. They had to solve it numerically. So, you know, I was on the phone today with someone who has an idea that they want to model the basin of drainage for the city of Houston. Is this a petroleum engineering problem? Sorry? It's a hydrology problem, correct. But we solve much more complicated problems than this every day. We solve problems that are 1,000 times more complicated than this every day. Maybe 1,000,000 times more complicated. But why is this problem going to be very difficult to solve? You're walking around it. Think about it. You have multiple sources and sinks, which you cannot define. Have you guys looked at a map of Houston lately? Anybody grow up in Houston? You did? Where'd you grow up? West. Okay, so Addicks and Barker reservoirs. Do you know that every drop of water that goes out of there goes through Buffalo Bayou? Is that a really good idea? So as you move towards the city in Buffalo Bayou, let's say that Alex and Tom decided we're going to build a canal. I didn't say a wall, a canal. And we're going to build a canal that will tolerate 100 inches of rain in a very short period of time. Okay? Who's between us and the ship channel? Memorial, River Oaks, and downtown Houston. How many billions of, let's call it what it is. How many trillions of dollars of real estate lies between those two reservoirs and the ship channel? That's where I think this person's going to have a really hard time selling this. When were those reservoirs put in? In the 1940s. So back then, okay. But how much will it cost to clean up Harvey? Rough estimates. Real estimates, not what you read on CNN or Fox. A couple of $100 billion at least. That's how much people have been put out. How do you think you'd sell an investment of $1 trillion in a canal? It'd be the largest construction project in the world for a long time to come, and all to protect against 1,000-year rainfall. Okay. Is it worth it? But what if you could model this instead? And what if you could show the choke points in the system? Okay, can we do that? Sure we can. It's a very novel idea, and he doesn't want to make any money off of it. He just wants to model it. It's a relatively simple problem. Tell me something that I don't know. You're within 2 miles of the Brazos River. Why not move the water that way? Instead, you move it 20 miles east when you could move it 2 miles west. Maybe it'd be a better investment to go that direction. We're off subject, but this is what we do. We look at these kinds of systems and we model them. You think petroleum engineers are going to stand in line for this problem? How many of you have taken a hydrology class? Nobody. I did when I was your age. I thought easy A, no problem. Equations are the same as we use. I was a little wrong. I did make an A, but I came out of there with a profound respect for hydrologists. So, my advice is we better consult them. They have the entire system mapped. Okay? All right. Again, 5 equations. Number 1, mass balance. Number 2, equation of motion. Number 3, equation of state. Number 4, constitutive equation. Number 5, equation of energy. Knock off the last 2, and we're going to start putting some things together. And I do apologize, it's very small. I'll use the mouse, especially for the distance learning people. This is our mass balance equation. This is Darcy's law. We will go on ahead and eliminate the gravity term, and we'll assume horizontal behavior, and we will insert that equation number 3 into equation number 2. We'll eliminate the vertical component or the gravity component, and now we have del dot the quantity rho k over mu del p is equal to the partial derivative with respect to time of porosity multiplied by density. This is very, very, very straightforward. You have a derivative operator on the left-hand side. You have a derivative operator on the right-hand side. Del dot alpha is defined as the partial derivative, of A, the partial derivative of A with respect to y, which could be anything, and then the gradient of y. So, okay, no problem there. Del dot del A for the linear flow case is going to be written as del squared A, and there'll be a second derivative with respect to x, second derivative with respect to y, second derivative with respect to z. For radial flow, del dot del A is again the same nomenclature, del squared A, but now we have 1 over r, d by dr, r dA dr. Do you guys remember this from last night? Yes. And then we have this term, which is actually the tangential component. So if fluid could move, we always think of fluid coming in a radial system as converging, only being linear converging radial flow, but there could be a tangential component, and there could also be a vertical component. Of course, we're going to ignore those. Okay? What's the likelihood of having tangential flow? Sorry? It would have to be a heterogeneous system, and we probably would not model it this way. Okay? How do you do it now? You model it as a linear system with heterogeneities in different blocks, right? Or you may use a PEBI grid, which has an unstructured grid, but you would not model it as rings or something like that. There was an enormous amount of work in the early 1990s on modeling things as concentric rings. Obviously, God or whatever force rules the universe does not make concentric ring permeability reservoirs. But the thought behind this was if you could come up with a method of estimating the permeability distribution with the concept of rings, then you could extrapolate it somehow to the concept of a random permeability field. Enormous amount of work was done on that. Okay. So we work our way down from equation 5, and we have del dot rho del P. And of course, we move the viscosity and permeability to the right-hand side because we assumed it was constant. So we assume that the permeability and the viscosity are constant. Move those to the right-hand side. And then we start expanding things. Okay. So the first thing we do is we use the chain rule, and we expand this derivative. The second thing we do is use the product rule and expand this. The del dot operator is a derivative operator just like anything else. So del dot rho del P becomes del dot rho del P rho del dot del P. What's the definition of del dot rho? Well, it's going to be del dot rho is going to be the derivative of density with respect to y, and then the gradient of y. What is our variable class? It's P. So for del dot rho, it becomes the derivative of density with respect to pressure multiplied by the pressure gradient. That one's easy enough. And you can see exactly that that is going to become our friend right here eventually. It's not obvious now, but that's exactly what's going to happen. This term is going to become that. Now on the right-hand side, when we take the partial derivative with respect to pressure of porosity and density, what's going to happen here is we're going to then use the product rule and expand this. And fortunately, whatever force you believe in the universe, some nice things happen. Okay, so again, the del dot rho del P becomes this term, which is d rho dP multiplied by the gradient squared. The only thing we need to do now is divide by 1 over rho, and that gives us compressibility multiplied by gradient squared. Okay, we'll get to that in a minute. Rho del dot del P is just going to be rho del squared P, no problem. So that gives us this term moves to here, this term moves to here, and we still have not expanded this. We now need to expand this. Using the product rule, first derivative term is going to be the derivative of density with respect to pressure multiplied by porosity. The derivative of porosity multiplied with respect to porosity, multiplied by density. Okay, so we factor out the rho phi, and we're left with 1 over rho d phi dp, 1 over phi d phi dp. Sorry, I said that wrong. 1 over rho d rho dp, 1 over phi d phi dp. And what is that, class? What is the name of this variable? That's fluid compressibility, and this is rock compressibility. Okay, so fluid compressibility is given by C, rock compressibility is given by C sub F, and then we have this expression that says this derivative is equal to the porosity multiplied by the density multiplied by this compressibility term. Now, it's single phase, so we simply add C and C sub F, and that gives us C sub T. When we substitute this back into the expression, our density term is here, our density term is here, and we have a derivative of density with respect to pressure. So if we just divide through by density, that eliminates that term and that term, which is nice, and it puts it all over here. So that's 1 over rho d rho dP, then del P squared, and then del squared P, and then this term. Now over here, we assume that porosity, viscosity, compressibility, and permeability are all constants. So this is linear on the right-hand side. Unfortunately, on the left-hand side, once we substitute the definition of fluid compressibility, we have this term. It is nonlinear. It is a function of pressure raised, the gradient in this case, but raised to a power other than 1. It's also multiplied by a function of pressure. And we're going to have to get rid of it somehow. Okay? So if we assume that we can get rid of it, then what will happen is, we'll only be left with this bit. So again, assume whatever assumptions we make, slightly compressible liquid, etc., we're going to end up with equation 16 as our final form. Any questions about this? Okay, so you've derived the diffusivity equation for a liquid. If I were a nice guy, I'd say we don't have to do the next 2 lectures, because we're not going to solve the diffusivity equation for gas. We're not going to solve the diffusivity equation for multi-phase flow. We're going to solve what? The simplest case, which is a diffusivity equation for a constant compressibility liquid. Now, I know you want me to be a nice guy, but it's not my DNA. Okay, so tomorrow night we're going to talk about gas. If you want to read ahead, there's a discussion about how to derive a liquid pseudo-pressure here, and that's certainly something you could do. I personally prefer not to do that. There are a few occasions when I have used a liquid pseudo-pressure, an oil pseudo-pressure, but for the most part I have not. Now, I will warn you that at least one vendor's software does use liquid pseudo-pressure, and they don't tell you. And of course they all use gas pseudo-pressure. And what I'm getting at is liquid pseudo-pressure sort of normalizes out or linearizes out one part of it. But they're also using an algorithm that is semi-numerical, so they're solving this problem in a semi-numerical fashion. So using pseudo-pressure probably ensures stability, but they're going to iterate anyway, and it's probably plenty accurate enough. I know that's going over your head, but what I'm telling you is that you have the assumption of a linear partial differential equation. So you use the solution for that linear partial differential equation, but you iterate on it at each step so that the fluid properties, in this case the oil properties, would be represented properly. Okay. For the gas case, it would be the same thing. You cannot solve the gas case analytically. You're going to, well, okay. If you look carefully, I think it's lecture 24 or 25, I propose a method for solving the gas case analytically. Who wants to take a shot? Mr. Liu, if I told you that you had to solve the gas case analytically, what would your first step be? See, this is so unfair because you've never even derived the gas case, much less how would you know how to solve it? Any ideas? Nothing, right? If we were to try to solve the gas diffusivity equation with the nonlinearity on the right-hand side, how would you do it? Okay, very good. You would assume a functional form or a functional relationship of the right-hand side nonlinearity. Okay. So that lecture we probably won't cover. We might. I don't know. It's really intricate and it's not trivial. It requires your brain to think about, some things it doesn't want to think about. And I had a vision whenever I solved it that you could use the Laplace transform to do this, and it did work, but you kind of have to hold your head sideways and think about it. There's another approach that was presented by a faculty member from Penn State, your good friend Dr. Ayala, and then another solution from a faculty member at a university in Brazil, and they both had a similar idea of a functional form for that right-hand side nonlinearity. Dr. Ayala's was a power law form. I don't remember what the guy from Brazil was. My idea was a little bit different because I was taking a Laplace domain. Again, way over your head, and I apologize for that. But when we get to it, what I want you to realize is solving a nonlinear equation, even in a semi-analytical form, is going to be really tough. You have to make some assumption. What would be the best assumption to make if you had to solve this thing? Pseudo-steady state flow. So because you would have the material balance equation, you would have the pseudo-steady state flow equation, and you could represent the system behavior, that nonlinearity, in a fashion where it could be solved. Now, it turns out that it also works during transient flow. But that's more of an academic problem. And again, we'll talk about that some other time. Okay, so an alternative, as I mentioned a moment ago, is to set up the diffusivity equations in these forms where you would have on the left-hand side KO mu O BO, and on the right-hand side porosity and BO kg mu g bg on the right hand side, phi and bg. And if you define the pseudo-pressure in this form, how do we know that the pseudo-pressure has to be that form, class? Nobody wants to take a shot? Mr. Desai, no idea? Okay, look at the diffusivity equation, guys. This part is the non-linearity. So it becomes the kernel of the pseudo-pressure, okay? And whenever we do the gas case, it's going to be P over mu Z over here. And so it becomes the kernel of the pseudo-pressure function. Okay. All right. Yes, Mr. Okay, where are you reading? Okay, where are we at? Sorry? Oh, here? This is a reference. Okay, thank you. Very good. Thank you for that. I prefer to define pseudo-pressure so that the units are always pressure. So I pick a normalizing condition. Most of the time it's going to be initial pressure, but it could be any pressure. So very good. You've discovered my little secret. Okay. And the reason that this is so important is because now this looks, smells, tastes like pressure. So any equation you derive for a liquid, if you use this form of pseudo-pressure, you're fine. Now, obviously, you have to pick your normalizing condition. And as I mentioned, the logical condition would be initial pressure. It could be bubble point. You know, you may decide. It's arbitrary. You can do whatever you want, but you just nailed it. You have to have a normalizing condition for the form that I've elected to use. If you do that, so what happens, and you can see, is whenever you substitute this into the diffusivity equation over here, you'll have it here, you'll have it here. This is just a big constant. And when you have the same constant on two sides of an equation, it just cancels out. Okay? That's the key. But very good catch. Absolutely, actually an extremely good catch. We apply a reference condition, and like I said, I call it normalizing here, but it'll be mu b over k evaluated at some pressure. So very good. It is not the constant. We're not assuming the behavior is constant. We're assuming the condition at one place. Okay. Very good. Who wants a final question? I want you guys to think very carefully. We could stop now and just go on and solve this thing. But I want to do the gas and I want to do the multi-phase. I know it's going to cost us an extra day now, and I apologize for that because I thought we could get them both done, gas and liquid, tonight. But we're out of time, and also I think your brains need to adjust a little bit. Tomorrow night will be weird, okay? So if you need some medication, or you want to bring a note from your doctor that you can put some earplugs in or something like that, that's fine. But I want you to come, even if it's osmosis that you learn this by. I want you to come. Tomorrow, you will learn how something excruciatingly complex can be made extraordinarily simple by just knowing which thread to pull. Okay? Do you guys understand what I'm saying? We are going to derive a diffusivity equation for pressure squared that is the ugliest thing you're ever going to see. But you can make the whole thing disappear by proper selection, proper setup. And nobody likes this. Nobody likes to set something up to where all the pieces, unlodge. And that's why tomorrow night's lecture is such a pain, because we'll do the same thing with the P over mu Z term as well. The pressure equation. Okay. I'm trying to think of how to get you enthusiastic for this, and I didn't do a very good job. It's once in your life where you're going to do something, where you're going to derive something that is so weird looking. Let me give you an example. Let's say we end up with a function of pressure inside of a logarithm and then you take the reciprocal of that, and then you take the derivative of that with respect to pressure. Everybody got that? So it's really ugly. You could even throw a square root in there if you want. Okay. But what if that thing is constant? The whole thing disintegrates. What's the derivative of a constant, class? 0. It doesn't matter what that constant is, but you can make the whole thing reduce by properly setting up the problem. Okay, and that's what we'll do tomorrow night. And don't worry, I'm not going to let my wife talk me into anything tomorrow night. I might even make her come in here and apologize to you. Would you guys like that? Yeah. Sorry? I couldn't hear you. She has. Yeah. She's got 2.5 degrees in petroleum engineering. Actually, she was never my student, but she sat through something similar to this. She wrote a couple of chapters in Dr. Lee's natural gas engineering textbook. I did as well. So it probably won't come back to her very easily since she's been a gynecologist for 24 years. But that's all right. Thanks for your little help there, Eric. Okay, everyone.